The world, so vast and unknown, is still a wonder for man. Since the dawn of time, we've looked up at the stars and wondered what lies behind the bright curtain of the night sky. It is not only curiosity that drives us to look up, but also a deep desire and inner desire to explore, conquer the unknown and push the boundaries of the possible. This perpetual motion has produced the greatest discoveries and advances, from the first astronomical observations to the development of modern space travel. But when we dream of crossing the stars, a question arises: how can we cross the great distances of the universe that lie between us and the other worlds? Will humans one day be able to travel beyond our solar system and explore the far reaches of the universe? These questions establish the essence of space exploration. Imagine a future where humans no longer feel the constraints of space and time, and travel to the distant stars is like sailing the ocean. This dream, once the exclusive domain of science fiction, may come true. A new era is dawning, one that sees spaceships traveling faster than the speed of the moon, traveling around the world and bringing distant worlds to us. Yesterday's science fiction is slowly becoming tomorrow's reality. Scientists around the world are on the verge of groundbreaking discoveries that could push the boundaries of space travel as we know it. Concepts that were once dismissed as grandiose are now being thoroughly investigated, and with each passing day we are closer to unlocking the secrets to traveling faster than the moon. But how close to crossing the final border? How much science fiction is science fact? To answer these questions, we need to dive into the heart of theoretical physics and explore the amazing ideas that may one day make travel faster than light. At the heart of the discussions about faster-than-light speed lies the big scientific question: is it possible to break the world's speed limit, the speed of light? According to Albert Einstein's theory of relativity, nothing can travel faster than light without requiring infinite energy. When an object approaches the speed of light, its mass increases, which means it must have a source of energy that cannot keep it going. This global speed limit has limited humanity to the slow crawl of conventional navigation systems, preventing us from truly exploring faraway places. For decades, scientists and engineers tried to overcome this seemingly insurmountable obstacle. How can we get to Mars and other solar systems when current technology is so slow? It seems the answer may not be moving fast, but bending space. This is where the idea of warp drive comes in, first popularized by science fiction and later explored in theoretical physics. The basic concept of the spinning wheel is simple and revolutionary. Instead of trying to go faster than light, why not bend space and time to send it faster than light? This fantasy, called fantasy, has become a legitimate research topic among physicists. The idea of compressing space at the front of the spacecraft and expanding at the back, creating a sort of blue bubble, has captured the imagination of the scientific community. A spaceship traveling through this bubble is able to surf the space wave faster than the speed of light without breaking the speed limit of the universe. This concept is based on Einstein's theory of general relativity, which explains how massive objects can influence the structure of space. The roots of this idea go back to the Mexican physicist Miguel Alcubierre, who in 1994 presented a theoretical model of faster-than-light travel. His theory, known as the Alcubierre station, posits that by manipulating spacetime, a spacecraft could travel more efficiently than the moon without violating the laws of physics. However, turning this conceptual model into reality poses a number of challenges, not the least of which is the need for extraneous matter, some kind of negative energy material needed to create and maintain the warp bubble. The Alcubierre station, while being tested, had many problems in theory and practice. One of the main obstacles is the desire for extraneous or negative energy. Manipulating spacetime on a scale necessary for faster-than-light travel would require enormous amounts of energy, far beyond anything available to humans today. To complicate matters, this force must be taken in the form of negative energy. A concept that is still thought of negative energy is a different concept in physics. This phenomenon is related to phenomena such as the Casimir effect, which occurs when two parallel, free metal plates are placed near each other in a vacuum. The space between the panels means that there is less energy to move around, which leads to the display of negative energy. But while negative energy has been demonstrated on a microscopic scale in the lab, using it on a large scale to power a warp drive is still a distant dream. Despite these challenges, the Warp Drive project continues to inspire researchers. Scientists such as Dr. Harold "Sonny" White, a former NASA physicist, have worked to refine the theoretical models behind warp drive and explore ways to travel faster than the Moon. Dr. White's work at NASA's EagleWorks laboratory led to the discovery of tiny bubbles, cosmic bubbles, small variations in spacetime that can be magnified for use in space. Dr. White's findings have sparked interest in traveling faster than the Moon, suggesting we are closer to the reality of a warp drive than previously thought. However, the road ahead is still long and full of challenges, and many researchers are skeptical about going faster than ever when it comes to health. To understand the challenges of space travel beyond the Moon, it helps to look at history and other considerations. Just as Concorde pushed the limits of what was possible in space travel, warp drive technology aims to push the limits of space travel. Just as Concorde faced many technical and economic problems, so did the concept of faster-than-light travel. However, Concorde is also a reminder of the human quest to break down barriers. Despite its retirement, Concorde's legacy has inspired new generations of engineers and scientists to continue exploring hypersonic and even supersonic travel. Likewise, the dream of faster-than-light travel and the spirit of innovation and determination that took Concorde to the sky are still alive. The ultimate goal of traveling beyond the Moon is not only to reach the distant planets of the solar system, but to explore the far reaches of the galaxy and beyond. Interstellar travel. The ability to travel between the stars has long existed in science fiction, from Star Trek to The Expanse. But while these fictional worlds feature interstellar travel as an adventure, it's far more complicated. The nearest star to Earth, Proxima Centauri, is more than 4 light-years away. With today's technology, it would take tens of thousands of years to achieve. Even our fastest spacecraft, the Parker Solar Probe, traveling at 700,000 kilometers per hour, will take more than 6,500 years to reach Proxima Centauri. The great distances involved in interstellar travel are beyond the reach of today's technology. However, the development of warp stations may change. By changing spacetime, we can travel great distances in space, and interstellar travel is possible in a human's lifetime. This opens up the opportunity to explore new star systems, discover habitable planets and establish colonies on distant worlds. But before embarking on such ambitious projects, there are still many questions to be answered. How does one generate the amount of energy needed to sustain a warp bubble? How to protect the spacecraft and its crew from the forces of rotation associated with spacetime? Perhaps most importantly, how do we ensure that faster-than-light travel is safe for humans? As we stand on the threshold of a new era in space exploration, it is worth reflecting on how far we have come and how far we still have to go. Traveling faster than the Moon is not easy, and it may take decades, if not centuries, to develop the necessary technology. Yet the dream of traversing the stars remains as powerful as ever. In the coming years, advances in fields like quantum physics, artificial intelligence, and propulsion technology will bring us closer to unlocking the mysteries of the universe. New generations of scientists and engineers will continue to push the boundaries of what is possible, driven by the same curiosity and determination that has propelled humanity forward for millennia. The development of faster-than-light travel may one day be seen as the crowning achievement of human civilization, a milestone that marks our transition from a species confined to a single planet to one that explores the galaxy. As we venture into the unknown, we will carry with us the hopes and dreams of generations past, forging a path through the cosmos and ensuring that humanity's legacy endures for millennia to come. In the words of the famous astronomer Carl Sagan, there is something wonderful out there waiting to be discovered. Maybe the amazing discovery will come not in the form of new knowledge, but in the form of progress that will allow us to reach out and touch the stars. The journey may be long, but the journey will be worth it. Although the dream of faster travel beyond the Moon is still a long way off, significant advances in related fields could one day pave the way for interstellar travel. One such area is the study of antimatter propagation. Antimatter, the most common form of matter, has the potential to become the most efficient energy source known to man. Matter and antimatter collide and annihilate each other, releasing enormous amounts of energy. In theory, this energy could be used to power a spacecraft, allowing it to reach unprecedented speeds. The topic has long been of interest to researchers, but presents many challenges. One of the biggest problems is the difficulty of producing and storing antimatter. Currently, we can only produce antibodies in particle accelerators, and safe storage is a major technical challenge. But if these obstacles can be overcome, antimatter production could revolutionize space travel, allowing us to take out stars in a fraction of the time it takes conventional propulsion methods. Another method of research is the study of wormholes. Wormholes, known as Einstein-Rosen bridges, are horizontal shortcuts through space that can travel faster than light. In theory, a spacecraft could enter a wormhole in one part of the universe and exit in another, traversing vast interstellar distances. Although wormholes have not been found in nature, they are solutions to the equations of general relativity, and some physicists believe they exist. But wormholes, like tar drives, present many theoretical and practical challenges. One of the main concerns is stability. Wormholes are thought to be very unstable and collapse before the spacecraft can pass through them. Also, building a wormhole to make the spacecraft travel a lot with a lot of energy may be more than necessary for a single revolution. Despite these challenges, the study of wormholes is an active area of research in theoretical physics. If wormholes can be stabilized and equipped for travel, they could provide faster-than-light travel and allow humans to explore the far reaches of the universe.